So, what if I told you there's a single rule book that explains everything? I mean, everything, from a baseball flying through the air to planets orbiting the sun. Well, today, we're going to open that rule book and unlock its secrets. Sir Isaac Newton's 3 laws of motion.
You know that feeling, right? The light turns green, the driver hits the gas, and you feel yourself get pushed back into your seat. That's not just some random sensation. That is a direct conversation with one of the most fundamental principles in all of physics. It's the universe following its own very specific rules.
See, none of this is chaos. It's a beautifully predictable system. And we're about to crack open Newton's rule book to really get why things start moving, why they stop, and, everything in between. But every great story needs a main character. And in the story of motion, that character is force. It's that simple. A force is just a push or a pull. It's the ultimate agent of change in the universe. If an object's speed or its direction is changing, you can bet a force is making it happen. It's why a soccer ball flies off your foot when you kick it, and it's why your chair is holding you up right now.
Okay, let's dive into Newton's first law. I like to think of this one as the universe's default setting. It basically describes what objects do when you just leave them alone, when all the forces are balanced out and there's no net force pushing them one way or the other. This classic little experiment shows it perfectly. When you flick that card, you're only applying a force to the card itself. The coin, well, it has this tendency to just stay put, so it resists that sudden change. It stays right where it was, and then gravity takes over, pulling it straight down into the glass. And that resistance to change? It has a name: inertia. You can honestly just think of it as an object's built-in stubbornness, or maybe laziness. Every single object with mass has it. An object sitting still wants to keep sitting still, and an object that's moving wants to keep moving in a straight line.
So how do you measure this inertia, this stubbornness? Well, that's where mass comes in. Mass is literally the measure of an object's inertia. The more mass something has, the more it fights back against any change to its motion. It's exactly why pushing a car is a serious workout, but pushing a bicycle is, no big deal. The car has way more mass, which means it has way more inertia.
And this brings us to a super important point we've got to get straight. Mass is not the same thing as weight. Your mass, the actual amount of stuff you're made of, is constant. It's the same on Earth, it's the same on the moon, it's the same floating out in deep space. Your weight, though, that's just a force of gravity pulling on your mass. So since the moon's gravity is a lot weaker, you'd weigh less there, but your mass and your inertia would be exactly the same.
All right, so if the first law is all about the status quo, the second law is where the action is. This is the engine of change. It tells us exactly what happens when an unbalanced force shows up to the party.
Okay, so take a look at these two situations. Imagine this person is pushing with the exact same amount of effort in both pictures. The crate on the left starts to move, sure, but the giant boulder on the right? It doesn't budge. So what gives? The secret is all in the relationship between force, mass, and acceleration.
And the answer is captured in one of the most elegant and powerful equations in all of science: force equals mass times acceleration. F equals ma. It's so simple, but it explains a truly staggering amount about how our physical world works. So let's just break that down really quick. The first part is totally intuitive. The harder you push something, the more it accelerates. Simple, right? More push equals more go. But the second part is what explains our boulder problem. Acceleration is inversely proportional to mass, which is a fancy way of saying that for the exact same push, an object with more mass, more stuff, is going to accelerate less. More stuff equals less go.
And that brings us to Newton's third law, and maybe his most profound one, the law of universal pushback. This one reveals a fundamental truth about the universe. Forces never, ever happen in isolation. They always, without a single exception, come in pairs.
The law itself is just elegant. For every action, there is an equal and opposite reaction. What that means is that anytime you push or pull on an object, that object is, at the very same moment, pushing or pulling back on you with the exact same amount of force. Just think about a monitor sitting on a desk. Thanks to gravity, the monitor is pushing down on the table. We can call that the action. At the exact same time, the table is pushing up on the monitor with an equal and opposite force. That's the reaction. If that reaction force wasn't there, the monitor would just fall straight through the table. Okay, so we have our 3 fundamental laws. That's the rule book for motion.
Now, let's meet the cast of characters. These are the specific, named forces that we run into every single day, and all of them play by Newton's rules.
We're going to focus on 4 of the most common players you see all the time. There's the force of gravity, which we feel is weight, the normal force, that's a surface pushing back, tension, which is the force you feel in a rope or a cable, and of course, good old friction, the force that always tries to stop things from moving.
We've actually already met the normal force. It's the perfect example of Newton's third law in action. Whenever an object sits on a surface, that surface pushes back. And that force is always perpendicular to the surface, which, by the way, is what normal means in physics. It's the reaction force that stops the book's weight from pulling it through the table.
Now let's talk about friction. So picture this. You're trying to slide a heavy trash can across the floor. You start pushing on it, but at first, nothing happens. Why? Well, because there's an invisible force pushing back against you. That is static friction. It's this clever, stubborn force that actually matches your push, getting stronger as you push harder, all to keep the object perfectly still.
But then, you give it that little extra bit of oomph, and it finally breaks free. It starts sliding. Now the resistance is still there, but it's changed. Now you're up against something called kinetic friction. And here's the key. Kinetic friction is almost always weaker than the maximum static friction you had to fight against to get it moving in the first place.
So what's actually going on? Well, this graph shows it perfectly. As you increase your push, right, the static friction force climbs up to match you. It goes right up that peak. But once you hit that absolute maximum static friction, boom, the can breaks free. And instantly the friction force drops down to that lower, constant value of kinetic friction. This right here is why it's always harder to get something heavy moving than it is to keep it moving.
So let's just boil it all down. Law number 1, objects are lazy. They have inertia. They want to keep doing what they're already doing. Law number 2, if you want to change that, you need a net force, and the magic formula is F equals ma. And law number 3, forces are never a one-way street. They're always a two-way conversation, an action and an equal opposite reaction.
And that leaves us with one last, kind of mind-bending thought to take away. According to Newton's third law, the force of Earth's gravity pulling you down is perfectly, exactly matched by your own gravitational force pulling the entire planet Earth up towards you. The forces are equal. So, why don't you see the Earth come rushing up to meet you when you jump? The answer is hidden all the way back in law number 2. Think about it.